Okay, so in the last class we are discussing about this model. Yes, audible. So order statistics we are discussing, and the thing is that the idea of this is we have to find out the ith smallest element. So ith smallest element we are trying to find out, and we raised a question that okay, whether order of n time algorithm existing or not, right? And the answer is yes. Two ways we can do that. One is this randomized divide and conquer algorithm, okay, and that will be running in expected running time. Expected running time is order of n, and there is again one deterministic algorithm existing, and that will be seeing after a short while, and that will also be running in this without expectation. This is a deterministic one, and this will be running in Tn equal to order of n time. So first let me give an idea of this randomized divide and conquer algorithm. Randomized algorithm is almost everywhere in computer science right now, okay, randomized algorithm, and this is so important paradigm of computer science research, okay, randomized algorithm. And this is we have to find out the ith smallest element, right? We have to find out the ith smallest element, okay. So this is a example you take, okay. Again as we are starting with this lecture, we can say that as we are using this Eric Deman and Professor Lyserson lecture, okay. So as I told you earlier as well, that this is from their course, okay. So this is from MIT OpenCourseWare, and this is 2005 course, but this is one of the best course, best programs I have seen, okay. So this is regarding algorithms, and especially the lecture slides they have made, it's excellent, okay. And we are trying to take the help of that at some for few of the lectures, okay, like this one as well. Okay, so we have to select the I equal to 7th smallest element here, okay, 7th smallest. So what we are doing here is this pivot. We are choosing one pivot, okay. And in our randomized algorithm, the previous slide, in the randomized one, what we'll be doing is we'll be choosing the pivot element random, okay. We'll be choosing the pivot element randomly, so it may be the first element like this, or any other elements, okay. So in randomized algorithm we choose the pivot random. Okay, now after choosing the pivot, say randomly I have chosen this pivot, and then around this we have to partition the list into two parts, okay. So first of all, this 10 I have to check whether it is less equal to or greater than the 6, and then accordingly I have to send it this side or this side. So as 10 is this side, we have got 10 here. So like this way, this every other elements will be compared with the pivot, and then we have to divide the list into two parts, right? And now once I have got this partition, okay, so this is our P, and this is our R, and this is our Q, okay. So how many elements will be there in this list? First of all, we have to check that whether this is this how many elements we are having here in this left hand side list, including this R. So this that might be R minus P. So this is P equal to 1 here, maybe this is R equal to 4 here, right? So how many elements will be there? 4 minus 1 plus 1, right? So this will be 4 again. So R minus P plus 1. These many elements will be there in this list, including this one, pivot 1, right? So now this I have got this K equal to, say, K equal to this R minus P plus 1. Then this is the kth position we are having. This 6 is in the kth position of this array, and that will be the kth smallest element. Okay? You see, this 6 is the 4th smallest element, right? And I have to check that I have to find out the 7th smallest element. 7th smallest element. Now this 4th smallest element and all these are not sorted. Okay, this is unsorted array. So during the partition it will not be sorted. It will only be giving the indication that these elements are less than or equal to these elements. Okay, as we are assuming that all elements are distinct, so these elements will be strictly less than this, and these elements will be greater than this. So that is the indication. It is not telling that these elements are sorted. Then the problem will be very trivial. Okay, so kth smallest element, so kth one we have got, and I have to check that I equal to 7th smallest element. So I have to check whether K equal to I or not. K equal to I. So here I am saying that, okay, K not equals to I. That means K equal to 4, but I equal to 7. Then what we got to do? There is no point recursing in this list, because these elements will be less than this. So any of these elements will be indexed by 1 to 3 here. Okay, first smallest may be there, second smallest may be there, third smallest may be there, like this. There may not be the case that in this side there will be 5th smallest element. Okay, so 5th smallest element, right? So this is how we are we have to put forward our logic, and then we will be searching the elements then definitely in this list. But in this list, which smallest element we have to search? Which smallest element? Which smallest element we have to search? So can anybody tell me that if I have to search right now, I have to search in this list? Then one of you say that which smallest element we will be searching here? Will it be 7th smallest element, or some other than 7th smallest, some other elements we have to search? Can anybody say? Hello? Hello? Can anybody say which smallest element? Who will be telling? Preeti, you tell me. You tell me. Which smallest element I will be searching in this list then? I haven't got K equals to, K not equals to I. That means it is not the 4th smallest element I am looking for. I am looking for the 7th smallest element. Then there is no point There is no point recursing in this list. Okay, because we will not be getting the fifth smallest element onwards in this list, because all elements will be less than this 6. Okay, so here in this list, so I minus kth smallest element, so this is 7, so this is our I, and this is our 4, that is k. So this is the third smallest element. We have to search here. Okay, third smallest element right now. We have to search in this list, but we have to search for third smallest element, right? So this is the way we have to proceed. Now completely I have to ignore this list, this left hand side including this one. Okay, and then I have to recurse this. It may be if I, instead of I equal to 7th, if I had to search the second smallest element, then I had to search in this list, and in that case I equals to 2 will be retained. Okay, because we are not excluding any other elements, because we are recursing in the left hand side. So that's how we proceed. Okay, and this is the randomized one. So this first, if p equals to q, that means one element we have to return. Okay, just a minute. We have to return. Otherwise, what we got to do, we have to have this partition. Okay, we have to have these pivot elements to be selected, and then k equal to r minus p plus 1, that I have shown you, that we have to find out. K will be the rank of this AR. That means which smallest element we are in right now with this pivot. And then if I equals to k, so I in our case it was 7 and k in our case it was 4. If I equals to k, then return that. That means that smallest element we are trying to find out. Other than this, if I less than k, then we have to search this smallest element I in the left hand side list. P to r minus 1. Else we have to return we have to recursively solve the right hand side list. Okay, r plus 1 to q, and with this smallest element I minus k. That means 7 minus 4. Okay, so this is the idea of this randomized divide and conquer algorithm. Okay, and now what could be the time complexity of this analysis? There is an expected running time analysis that we will not be discussing here. I discuss this, if time permits then I can. I discussed this in advanced algorithm class, or this MTech advanced algorithm class. Okay, so this is a very fantastic analysis is there, remarkable. Expected running time is order of n, but the intuition for analysis is this, that if we are lucky, then we might be having in one side, so we are having this list and we have got a pivot, and around that we have divided the list into two parts. Okay, so this is our pivot, and we have got this list and this list. Okay, so there is every possibility that this pivot will be dividing the list in 1:9 ratio. Okay, 1:9 ratio, and we are every time we are recursing as we are doing the worst case analysis. So that means if we are taking the 100 elements are there in the list, 100 elements, then this 1:9 ratio will be having that in this side in this side we will be having 10 elements, and in this side we will be having 90 elements, and every time in the bigger list I am recursing, okay, for finding the ith smallest element. And there is every possibility that will be returned this 1:9 ratio, the partition. So in that case, and I have shown you that in one side only, either this side or this side, I have to recurse, not the both side, right? So if I am assuming that, as we are doing worst case analysis, so we are assuming that every time we will be doing the recursion in the larger list, okay? So that's why this T9n by 10 is coming in that partition. With that partition we have to recurse, and as the partition you have seen that around this pivot, first of all we have to partition the list, so that will be taking theta n time, right? So in that case Tn will be equal to this T9n by 10 plus theta n. Okay, so this is an intuitive analysis if we are having this kind of partition, okay? But in the, as we will be dealing with expected running time, so we are not sure whether it will be coming 1:9. In some iteration it might be 1:9, in some iteration it might be say 50-50 division will be there, okay? And in other cases some other partitions might be there, okay? So we have to do some kind of we have to take the expected running time, okay, of all the iterations involved or all the possibilities involved, okay? So that will be consuming 1.5 class, so I'll be not discussing that thing here, and that is a very good interesting analysis. But here the intuition is telling, okay, maybe on an average, if we are lucky, then, and this lucky case will be there, because even if the 10:10 and 90 in one part 10 and one part 90, it's absolutely possible, okay? An unlucky case might be in one side we are having one element, and in another side we are having 99 elements. So in that case we are having this kind of recursion, Tn-1 plus theta n, and that will be theta n square. So in that case our algorithm, that we are randomly picking the pivot element and we are partitioning, if we are getting this partition, then it might be the case that we are landing into theta n square time running time, and that is not good, because that is worse than sorting. If I am sorting the elements and then I am picking the kth smallest, that will be running in order of n log n, okay? Okay, so this is they have analyzed it here, this expected running time, but that I am not doing here, okay? So that I am tracking now. Is it okay? Is it okay now? Is it okay? Is it okay? Okay, so this expected analysis is there, which I am not discussing here. If some of you are interested, then you can talk to me offline. Not coming. Not coming. What about others? What about others? Everybody hearing cracking noise? Nobody is listening? Sorry. Just a minute. Is it okay now? Is it okay? Is it okay now? Okay. Okay. So we are not discussing now, but we will be discussing another interesting one. That is, okay. So this summary of randomized order statistics selection is works fast, linear expected time, that as I have told you, linear expected running time, that is expected Tn equal to order of n. Excellent algorithm. Yes. Yes. Not coming. Okay. Maybe. Okay. So summary of this randomized order statistics: expected linear expected time, excellent algorithm in practice, but the worst case may be very bad, theta n square time, as we have discussed. Now the question is there an algorithm that runs in linear time in the worst case? Linear time in the worst case, okay, not the expected running time. We are not the randomized one we are looking for. And the answer is yes, that is due to this this algorithm, okay, that was proposed by them in 1973. Okay. And this is the idea is we have to generate the good pivot recursively. Okay, we have to generate a pivot recursively. So we have got a list. We have got a list of numbers. Okay, list of numbers, and the everything, the partitioning algorithm, as we have seen that, okay, if I am having 1:9 ratio, the partition, if we can ensure, then we are having, if we can analyze with that substitution method, with that recurrence Tn equal to T9n by 10 plus theta n, then the running time will be Tn equal to theta n. Okay. So is there a way to produce, always ensure that we will be having this 1:9, that means the balanced partition always. Okay, for this case the balanced partition, definitely this 1:9 will be doing the trick. If I am getting more, it is good, and we will be showing that we will be getting, with the methodology that we will be discussing, we will be getting more than sufficient more than satisfactory answer. That means the balanced partition definitely will be having almost this 3:7 ratio, almost we will be getting 3:7 ratio. We will be getting the partition. So that will be this one side will be having 30% always, and another side will be having 70%. Okay. So it is better than this 10, 10 and 90 case. Okay. So that's how this algorithm will be working fine. And the idea is we have to find a mechanism so that a good pivot might be found, and around that pivot we have to partition. So how to find out that pivot element, that is the challenge here. How to find out that pivot element? In the previous case we have randomly selected the pivot, but here we will be deterministically will be selecting the pivot, okay, with following few sequential steps we will be finding the pivot element, right? So the idea is we have to so these are the list of elements here, okay. So here we are having, say, this might be 10, this element might be, say, 10, this element might be, say, 30, this element might be 55, this element might be 3, this element might be 11, something like this. And all these elements are coming here, so you can think of they are coming here. They are coming, so these elements will be coming here, okay, these elements. And then the other 5 elements, these 5 elements will be coming here. All these will be having some values, maybe 20, maybe 31, maybe 45, maybe 9, maybe 15. So like this way, all these elements were there here, then these elements were there, okay, or were there, right? So all these elements were there, right? So I'm right now, I will not clutter the picture, okay. So what we got to do is we have to divide the list into groups of 5. So divide n elements into groups of 5. Divide n elements into groups of 5 and find the median of each 5 element group, right? So this, we have to have this, divide n elements into groups of 5, okay. So you see this group not having this 5 elements, so we can analyze keeping it, or we may exclude that. Even if we are excluding this, and even if we are getting a good partition, so that will be much better. So this groups of 5 elements we are having, groups of 5 elements, and then what we got to do is we have to find the median of each 5 element group. Say this group by say insertion sort, by say this insertion sort, right? We have to find out the median of this by insertion sort, and this, you see, this 5 elements group, only 5 elements, so constant number of elements. So constant number of elements, and we are running this insertion sort on this constant number, then it will be running in order of 1 time, mind you. So insertion sort will be running in, say, order of n square time whenever n is large, okay. So that is that point we have to take into account. If I am employing this if I am applying this quick sort on this, then also it will be running in this order of 1 time. So because these are constant number of elements, 5 elements, right? And the question is that, again, the question might be coming to you that why groups of 5? Why not groups of 3? Why not groups of 7? Why not groups of 9 or 8, whatever? Okay, so that may be answered afterwards, okay, but that is complicated analysis, right? Anyway, so these groups of 3 we will be having in the exercise, but if I am having any group of, say, j number of elements we have to have in our group, okay, then what will be happening? Anyway, so you see this, we had these elements 10, say 30, say 1, say 50, then say 80, something like this. Now what we got to do is we have to sort this element by insertion sort, okay. So it will be coming as 1, then 10, then 30, then 50, then 80. So these elements, so here this element will be 1, this element will be 1, this element, this element will be 10, this element will be 30, this element will be 50, and this element will be 80. After this insertion sort, this will be the case, okay. So we have to divide the list. We have to divide the list into groups of 5 like this, and then on each group we have to run this, we have to run this insertion sort, and then we have to find the median of each 5 element group. So what is the median if I am having, say, 5 elements? So one answer is that why I am going for this odd number of elements 3, 5, 7, 9, because we will be having one median, so there will be no ambiguity in that case, maybe, right? So this will be the median of this list, okay. So this list could be, say, 20, say 35, say 40, say 65, say 90. So you see, so here you see this this one, and this one is connected by an arrow, so this is a greater element and this is a lesser element. As you see from the example, that 30 to 10 I am going with the arrow, and 30 to 1 I am going from the median, and here 50 to median 30, so arrow will be this side, and then maybe here 80 to 30. So this is the way. Here also the same thing. So this is 40 to 35, 40 to 20, 65 to 40, then 90 to 40. So like this way we have to have all these elements, and we have to find out the median element of each group, median element. So this will be some number, this may be some number. So here you see this may be okay, some smaller number I can take, maybe 5, maybe here 9 I haven't taken, so 9 maybe I can take, then I can take 19, then I can take 100, then I can take 120, something like this. So you see 19 is there, 40 is here, 30 is here. So these are the medians we are having. So you have to extract the medians. See, if I am having say 1000 elements, okay, 1000 elements, can anybody tell how many groups we will be having? 1000 elements, how many groups we will be having? 200, yes. So this last 4 elements, this is for analysis purpose. Okay, you can sort this also. You can sort this for, if for this, so this I am ignoring this because of the analysis purpose, and whenever you will be implementing, at that time you will be sorting this also. You will be sorting this also, and you will be assuming that you are taking the lower median, and then this form, maybe this guy will be selected. So if this is say 130, 140, 150, 160, something like this, then 140 guy will be there as the median. So during the implementation, that you have to take into account as well. If you are writing any code, then this element you take into account as well. For the analysis purpose, we are showing that even if I am ignoring this, but still I am getting the good result. Okay. So this we are having 1000 divided by 5, we are having 200 such groups. So one group will be providing one median. So 200 such medians we will be having, right? So then what we got to do? We have to find out the median of these medians. Okay, we have to recursively select the median x of the n by 5 floor group medians. That has to be pivot, that you will be having as the pivot. So even if means whenever you are implementing, if you are wanting that you will be ignoring this, then also it will be working. Okay, so don't worry for that. If you are trying to include that, that also you can do, and even if you are not trying to include that in your code, that also, that trick also will be doing. So analysis will be showing that if you ignore this, then we don't have any kind of problem. So we have to find out the median. Right now we have to find out these are the medians. Okay, and we have to find out the medians of medians. So what we got to do here right now, we have to extract these 200 elements. We have to extract these 200 yellow elements. Okay, so these yellow one we have to extract. We have to extract these yellow one, 200 such elements are there, and then what we got to do, we have to find out the medians of again we have to divide these 200 elements into groups of 5. Okay, 200 elements into groups of 5. So 200 elements divided by 5, how many such elements we are having? 40 elements in the next step, and then 40 elements again we have to divide it into groups of 5. Okay, so 40 elements, 1 2 3 4 5 6 7 8. So 40 elements means these many elements. Okay, so at 40 elements we have to find out, and then we will be having so 1 2 3 4 5 6 7 8 groups, and then we have to again divide it into groups of 5, and then we can have trivial list, and we can find out by insertion sorting, we can find out the median of medians of that. So that means median of medians we are trying to find out. So first of all we have to groups of 5, and then we have to extract the medians, and then those medians will be our elements in the array, and then again we have to recursively solve the median of that 200 elements, and then those medians we have to extract, and then we have to again recursively solve that to find out the ultimate median, which we call the median of medians. Okay, so this median we have to find out. So in this case x will be our median, maybe we are taking this lower median. Okay, so x will be the median. So here this is the way we have to find out the median of median, and this x is the pivot element. So this x will be used as the pivot element, and around that pivot element we have to, so we have to go back. Okay, so okay, we had elements here, we had elements here, we had elements here, all these elements we had here, then all these elements we had here, so on. Then after finding this x, what we got to do is we have to compare. Now I have got the pivot element. Now each one will have to be compared with that x, and we have to find out. So this is x. If this guy is less than this, then this guy will be coming here. If this guy is greater than this, then this guy will be coming there somewhere. So like that way, around this x, we have to divide this whole list into two parts. This part and this part, right? And then we have to recursively solve, depending on which ith smallest element I am trying to find out, right? So the same procedure that we have to check we have to find out the rank of this x, and then that R means how many elements we are having, we have to find out, and then depending on that, so this k is R minus p plus 1, so that we have to find out. And then again, depending on this ith smallest element, we have to, in this list, if I have to recurse, then I have to find out the ith smallest element in that list. If I have to recurse here, then I minus kth smallest element in that list. So that procedure will be remaining the same. Only thing is changed from the randomized one is that we have toiled hard to get this pivot x. We have toiled hard to get this pivot x so that the partition will be balanced. Now in the next class we will be seeing that, okay, if I am finding the pivot by following the method of groups of 5 and then extracting the median and then finding the median of median, then we will be having a good partition. Which will be resulting order of n times algorithm. Okay, so that analysis we will see in the next class. Now if you have any question, you can ask me.